All right, guys, so this is going to be electrons as waves. So first we did electrons with Bohr, right? Then we did waves and wave calculations for frequency and wavelength, and we did the flame test lab. And now we're going to talk about if electrons acted like waves instead of little particles, all right? So far, like I said, we pictured electrons as little planets orbiting the nucleus, right? This was our Bohr model. How many electrons go in the first shell? 2. How many go in the next shell? And the next shell? All right. So that was a great model, and we still use it for some purposes. But now we kind of have a better model. All right. So now we have what we call the quantum mechanical model, where Rutherford and Bohr's model focused around describing the path of the electron like a nucleus, and the electrons were like little particles, like little baseballs or little planets that were circling around, right? Now we're moving up from there. We know Bohr had a better picture of the atom, but it still wasn't the whole thing. So now we have our physicist Erwin Schrödinger comes onto the scene, and he's the first one to say, well, much like light can be a particle or a wave, an electron can be a particle or a wave. All right, so the modern description of electrons in atoms comes from the quantum mechanical model, which comes from Schrödinger's equation, which you can see, which we are not going to go into. Yay, right? We're not going to solve anything using Schrödinger's equation. Okay, here was his main piece of evidence, is when you look at the diffraction of light, okay, you get this noticeable concentric circle picture. And when he did the same thing with electrons, he was like, whoa, like this looks almost identical. Okay, so he said not only can light be a particle, which we call a photon, and it can also act as a wave, an electron can act like a particle, or it can act like a wave. All right? Now, the quantum mechanical model is the model that determined the allowed energies an electron can have and how likely it is to find the electron in various locations around the nucleus. Schrödinger said it's great to have this idea that they're in a shell and here they are, like little dots, but that's not really the whole picture. These are moving at super high speeds. So it's more likely that you're trying to pinpoint an electron that's moving around the nucleus, much like trying to pinpoint a fan blade when it's turned on high, right? You can never just see that exact fan blade because once it's at that location, it's already moved, right? So you kind of see this pattern on the right where it's denser, it's more likely the fan blade is, but overall you cannot pinpoint it at any exact moment because as soon as you have pinpointed it, it's already moved. All right, so the new drawing of this, instead of drawing it like little planets, is to show it as a fuzzy cloud. So the probability of finding an electron within a certain volume of space, this is much more three-dimensional, is represented by a fuzzy cloud, and the darker areas where the cloud is the more likely you are to try and find an electron in that spot. All right, not too bad. Okay, we've all stared at a ceiling fan out of boredom, right? And you like see the darker areas and the lighter area. You know what I'm talking about, okay? I hope. All right, perfect. So we call those areas where electrons are more likely to reside orbitals. All right, so we had orbits with Bohr. With the new one, we have orbitals. An orbital is often thought of a region of space in which there is a high probability of finding an electron. Of course, our nucleus is positively charged, and that is going to attract our negatively charged electrons. So there tends to be a denser area of electrons closer to the nucleus, and it gets a little weaker as you go out. So this would be our orbital, and all of these blue dots are everywhere an electron has visited in that point in time. Now, in quantum mechanics, our orbital is defined as the electron cloud, and this is the region of space where there's 90% probability of finding an electron, and we can see how it's so much darker towards the middle and the outside, and that's kind of that cloud view. Not too bad, right? Are we good? Orbital equals electron cloud. Did you guys get that in your notes? Perfect. Okay, so there are 4 different kind of orbitals. There's S orbital, which looks like a sphere. P orbitals, which look dumbbell shaped, which look dumb. They just look dumb. Bell shaped. There we go. We have D orbitals, which are these like overlapping clover leaf. And so we have S, P, D, and then there's also F orbitals, which look like literal, I don't know, flowers. And they are going to build on each other at different energy levels. All right. Now, we could continue talking about this in this format, where we're going to talk about the energy levels and the sublevels and the letter of the sublevel, etc. But I think it's much easier to do this in terms of an analogy. All right. So I'm going to try and make this a little more fun, because it's a lot of information. So instead of just learning it straight electrons, I'm going to try and make it a little more interesting, okay? We're going to say electrons are going to college. Sound good? Okay. Just like students are going to go in dorm rooms, electrons are going to be assigned to a specific orbital in the electron configuration. Okie dokie? This is Oregon State University. This is actually where I went and did my undergrad. This is what it looks like. It's a very pretty school. It looks like an Ivy League school. It is not an Ivy League school, but it looks all pretty and brick and like, oh, it's so cool. Okay, it is a big school. It's a D1. We're in the Pac-12, right? It's a big school. So your objective is to be able to determine the electron configuration for an element by using the chart method and the periodic table. Here we go. So this should be the second half of your notes page. And you can see electron configurations are like dorm assignments. That's what we're going to pretend. Both electrons, and students need a place to, there's your fill in the blank, live. And we're rocking and rolling now. This is the dorm that I actually lived in. It was called Callahan. You'll see it is not the nicest dorm that you could live in, but it was cheap for a reason, okay? And our orbitals for electrons are going to be like the dorm rooms for our students in this analogy, all right? So whenever I say room, it's the same thing as an orbital. Whenever I say orbital, you can think of it as the room. The electrons themselves are going to be our students, and here we go. All right, so there are 4 types of rooms. And do you guys see on your pink paper where it says like S room? I want you to draw this single box, okay? And then in the P, how many boxes are there? 3. And then in the D, it's 5. It's kind of nice, they're odd numbers. And then in the in the F block, you're going to draw 7 rooms. So there are 4 different types of dorm rooms, 4 different types of orbitals. S, P, D, F. We're going to call these the super nice room, the pretty good room, the dumpy room, and the fantastically bad room. We got to keep it school friendly. Fantastically bad. When you have a super nice room, there's only one of them because they're really big and they're really expensive. All right? 3 pretty good rooms fit in about the same space as a super nice room. You can squeeze 5 dumpy rooms in there, or 7 fantastically bad rooms, okay? Because they are so tiny, you're like squishing students or electrons in there like sardines at that point. Okie dokie. Now, let's learn our rules. So the S orbital is our super nice dorm room, okay? And there's only one of these on every floor. There's only one S orbital on every energy level. So on energy level 1, you have 1s. Energy level 2, 2s. Energy level 3, 3s. There we go. And you can see this is an actual dorm that you can live in at Oregon State University. Look at that. You get a living room with a couch and a TV. You get a kitchenette. Okay, it has a sink and a place for your mini fridge. Each person gets their own like bedroom setup. There's 2 private bathrooms, one right here and one right here, okay? That is a super room. Miss Parker did not live in a super room, okay? But that's a fancy super room. Here would be our super room in our electron configuration diagram. These are all super rooms, and you can see there's only one on every energy level. There's only one on every floor of our dorm, okay? Now, then we have our pretty good room, which always comes in a set of how many rooms? 3, very good. And these are only available on floors 2 and higher. So in your little chart, you're gonna write only on 2nd and up, and there are 3 per floor. And this is what the pretty good rooms look like. You can see you get your own little living area in here. Most people have their desks and maybe like a little TV and a couch or whatever. All right, you get your own little sleeping room, which is nice because then if somebody's up late doing homework or watching TV, the other person can sleep, right? In the quiet. You get a walk-in closet. Ooh, you fancy now, okay? So pretty good room. They're pretty big, all right? You can see this is 17 feet by 15 feet. So it's a sizable room. Okay, it's pretty nice. I did not live in a pretty good room either. Okay. Now, we have our next room, the D orbital, which is the dumpy dorm rooms, okay? This is the one I lived in. That's not me, and that's not my stuff, but that is exactly what my room looked like when I lived at Oregon State, okay? And these are only on what floor? The 3rd floor and up, and they always come in a set of 5 rooms. You can see this room is 12 by 13, and it includes 2 beds, 2 closets, and 2 desks. And if you were on that bed and you wanted to pass chips to your roommate in her bed, you wouldn't even have to move. You just like this, okay? No problem. This is the door to the window is 13 feet. You consider most of these beds are 6 feet long. You are literally living wall to wall, all right? They're cheap. They're not that bad, okay? But guess where the bathroom is? Down the hall. Everyone uses the bathroom and the shower is down the hall. There's 1 per floor. Yay. Yeah, not quite the same as that cushy living room with the kitchenette. Is there a kitchenette in this? Absolutely not. Okay. So these are the dumpy rooms. Lastly, we have our fantastically bad rooms. And if it looks like a little prison cell, doesn't it? You get like a bed and a desk and a dresser. And that's it, okay? They only are found on the 4th energy level or floor and up, and they always come in a set of 7 rooms at a time. All right? And you can see that's pretty lame looking. I actually don't think they have these anymore. I think they tore down this building, and now they only have the nicer rooms. I don't even think they have my room anymore. Sad. That's what happens when you get old. All right, so the orbital is like the electron dorm room. And these rooms are the rooms that electrons can pick from, okay? Now, there are some housing rules that apply. We do not just fill them up in any order that we want, okay? The 3 rules we have to complete when we are doing electrons or housing assignments is Pauli exclusion principle, Aufbau principle, and Hund's rule, okay? Now, the first rule, Aufbau's principle, okay? Electrons fill the lowest energy orbitals first. Electrons fill the lowest energy orbitals first. This is actually known in chemistry as the lazy tenant rule. Meaning, in our analogy, we're going to think of this as there's no elevator in the dorm. Okay, like Big Bang Theory, it's always broken. And that was absolutely true in my dorm, and I was on the 6th floor. You move into a 6th floor dorm with no elevator, it sucked. Okay? So what we're saying is we are always going to fill from the bottom floor up. We are always going to fill from the first energy level closest to the nucleus up. All right? Easy peasy. Rule number 1, taken care of. We all good with that? Perfect. Rule number 2, Pauli exclusion principle. Each orbital can hold 2 electrons with opposite spins. Each orbital can hold 2 electrons with opposite spins. For our analogy, we are going to pretend each room has a bunk bed. You're going to put someone in the top bunk and someone in the bottom bunk, right? It would be weird if you meet your roommate for the first time and you're like, I'll share the top bunk with you. They may not like that. So Pauli exclusion, okay, 2 per room. 1 is up, 1 is down. All good? Okay. Third rule, Hund's rule. Within a sublevel, place 1 electron per orbital before pairing them. In other words, students would rather have their own room before they get a roommate, which is usually true. So we're going to assign, let's say we're in a P block of 3 rooms. We're going to assign each person a top bunk, and then if we still have electrons, then we'll start adding bottom bunks, okay? And we'll practice this, don't worry. All right, so there is a cheater trick chart that helps us assign all of the rooms while fulfilling all 3 rules, Aufbau, Hund's, and Pauli exclusion, okay? So I'm going to teach you how to draw it, and then we're going to use it every time we do these electron configurations to make it a little bit easier. It's also on me behind the board, but I want you to listen and follow along with me up here first, okay? Because it's very easy to memorize. So we're going to draw this like a pyramid. We're going to start with 1s, and we're going to add each room type on until we get our little pyramid shape, okay? Do you guys remember what are the orbital shapes called? We have S. What's the next kind? P. What's the next kind?
D.
And? Perfect. And I always think this is easy to remember. Maybe because I'm a nerd, I always think of a PDF. So it's just SPDF. Don't make fun of me. Okay, let's practice this. All right, guys. So our first floor is going to have 1s. That's all that goes on the first floor. Okay. The second floor is going to get 1s room. And I'm going to make this like a little pyramid. It also gets 1 p room. Now we're going to make our third floor. So the third floor is going to get 3s, 3p. We got to add on the next kind of room, which is 3d. Perfect. Now we're going to go to our next floor, which is 4. And we're going to do 4s, 4p, 4d, and 4f. Did we make our pyramid? Now you just repeat. 5s, 5p, 5d, 5f, 6s, 6p, 6d, 6f, and we'll just call it good at 7s because I'm out of room. I'm out of room. That's a 7s down there. Now we have to fill diagonally to make sure that students get the nicest room on the lowest floor without a roommate. Those are our 3 goals, okay? So you're not going to fill this 1s, 2s, 2p, 3. You're not going in that order. We have to go in diagonal order, all right? So here you're going to draw your diagonals. I'll go green, okay? So we're going to fill 1s first. Then you're going to fill, 2s. Then you're going to fill 2p and then 3s, because you'd rather have a pretty good room on the second floor. Then we can get super nice room on the third floor. Then we're going to fill Any guesses? Yup. 3D. Yep. Love it. Then we get 45P6S, 4F5D6P7S, so on and so forth. So you're going to fill in the diagonal order. Do not read this straight across. All right, so we just did this, and we're going to practice some notation. So let's see what this looks like when I actually give you a problem, okay? We're going to do the orbital diagram and the electron configuration. So let's say I have oxygen, okay? So go ahead and write oxygen on your paper. Oxygen is element number 8 on your periodic table, which means it has how many electrons? 8. Perfect. Now we're going to use our little diagram. You guys have it on a Post-it note now, right? I'm going to write it up here just for convenience sake. All right. So we are going to start by filling our 1S room, right? We have to follow the diagonal. So we have 1S, and S has one box. And how many kids fit in that box? 1 on the top bunk and 1 on the bottom bunk gives me 2. Does that make sense to everybody? So out of my 8 electrons, how many did I just use up? 2. Which means I still need to assign how many more? 6. So I did 1S. We assigned 2 electrons to it. What's the next room that I fill? 2S. So I'm going to put a 2S here. Has 1 box. How many kids can fit in there? 2. 1 on the top bunk and 1 on the bottom bunk. So I put 2 kids in there. We used up 2 more electrons. How many electrons do I have left? 4. What is the next room that I fill? 2P, okay? How many rooms come in a P block? Very good, 3. Now remember, we're going to give each kid their own room first, right? So I'm going to do top bunk, top bunk, top bunk. I used up how many electrons to do that? 3. So I still have 1 left. So my first one's going to get a roommate. It's going to get a bottom bunk, so we used up that last electron. I'm at 0. So how many electrons did I actually put in the 2p orbital? 4. So my answer up here is 4. This sequence of numbers is your electron configuration, if that's what I'm asking for. These boxes are what we call an orbital diagram. And that's it. So if you flip your paper over, there are some practice problems for you to work on.